All right, so today we're looking at continuity. If you're in class, this is a warm-up we did. If you weren't in class, you have a chance to look at this and try it yourself. The whole idea is you're finding what the function value is at A, what the function value is at A, what the limit as you approach from the left is at A, what the limit as you approach is supposed to be from the right is at A, and what the actual limit is at A. And then I want you to come up with the idea of, is this continuous? Why not? Just come up with a thought process for it, because you don't know what continuity is yet. I won't go over the answers, but you can always ask me later, and you'll be able to find the answers at the end of this lesson. Okay? So, a continuous function. A function is continuous if and only if. That's what this IFF means. The first thing is the function of exists. That means f of a is equal to some number, some finite number. Okay? Second, the limit exists. That means the limit as x approaches a from the left of f of x is equal to the limit as x approaches a from the right of f of x. So the limit exists. Lastly, the limit is equal to the function. So that means the limit as x approaches a of f of x is equal to f of a. Okay? Now, for most continuous functions, this is not going to be an issue. You're just going to plug in the value of a and you'll get the function's value. It should give you everything. All right? So the issue shows when we look at things like this, some piecewise functions. So let's look at this in pieces. First, we look at number one, f of a. Now, this says we're looking, is it continuous at x equals 1? So f of 1. Is there a value we can get when we plug in 1 here? Well, yeah, it says when x is equal to 1, we use this function. And so this is 2 times 1, which is equal to 2. Boom, gotcha. The function exists. Then we move to part 2. The limit. Does the limit exist? So we've done a few one-sided limits like this before. So limit as x approaches 1 from the left of f of x. Limit as x approaches 1 from the right of f of x. So if we look at the left, this is the left side here. These are the x values that are less than 1. So we're looking at the limit as x approaches 1 from the left of x squared plus 1. We'll plug in 1. Hey, look, that gives us 2. Limit as x approaches 1 from the right of, this is the right side of 2x. Plug in 1, that gives us 2. Does the limit from the left and the right equal each other? Yes. So the limit as x approaches 1 of f of x is equal to 2. So function exists, the limit exists. Our third step is to check, does the function equal to limit? So does f of 1 equal the limit as x approaches 1 of f of x? Well, f of 1 was equal to 2. The limit was equal to 2. Those are equal. This is what we call the three-step test for continuity. Now, there are a lot of cases where it might just ask, is this continuous? And in those cases, you're looking for discontinuities. And we'll talk about discontinuities in a bit. For now, if it's saying, is it continuous at a specific point, that's all you're looking for. Okay? So, give you a second to look at this, figure out, is this continuous? And you can play the video back once you figured it out. All right, so three-step test. 1, we're looking at g of 4. Well, here's where x is equal to 4, so that's square root of 4, which is equal to 2. 2, we're looking at the limit from the left and the right, so limit as x approaches 4 from the left of g of x. Here's the left side. Plug in 4, we get 1. Limit as x approaches 4 from the right side. This is the right. That equals 2. In this case, the limit as x approaches 4 from the left of g of x is not equal to the limit as x approaches 4 from the right of g of x. So it is not continuous. We do not have to keep checking. Once we reach not continuous, we don't have to check anything else. Okay? Next, we're finding a so that f of x is continuous. Now, this is a case where we're trying to make the function continuous. Now, this is a very simple process. If we want to make the function continuous, we want to make the left and right equal each other when we plug in x equals -2. Because by plugging in x equals -2, we're getting the function value. And by making the left and right equal, we're getting the limits value. All right, so we're making them equal when we plug in the x. So we want to say x cubed minus x minus 3 equals ax squared minus 2x plus 3. And we want to plug in -2. Now here's where we get a lot of issues here. We're looking for a, so that -2 is being plugged into x. So there's -2 cubed minus -2 minus 3 equals a times -2 squared minus 2 times -2 plus 3. So this is -8 plus 2 minus 3 equals 4a plus 4 plus 3. So it's -6 minus 3 is -9 equals 4a plus 7. Subtract the 7, -16 equals 4a, a equals -4. And there we go. We found a so that f of x is continuous. All right, moving on to the next one. Now we're talking about discontinuities. Now, for the most part, discontinuities are anywhere where one of those three things happen. The function doesn't exist, the limit doesn't equal the left or the right, or the function doesn't equal the limit. Now, the type of problems you're going to see that are asking about discontinuities are usually going to be one of two things. Either piecewise functions, where you're having to look, does the limit from the left and the right equal that specific x value? Which those aren't too hard, you're just plugging in the x and seeing. Or problems like this. Now, you need to think to yourself, where would a discontinuity occur at any of these problems? They all have a very similar answer. I'm not asking for a specific x, I'm asking for the idea of an x. They would all occur at whatever x makes the denominator equal to 0. Okay? Now, this leads to two different types of discontinuities. A removable discontinuity and a non-removable discontinuity. A removable discontinuity is a discontinuity in which if we put a point on the graph where the discontinuity was, it would be continuous. In other words, this is a discontinuity where the limit still exists, or where there's just a hole. Non-removable discontinuities are places where that can't happen, where even when a point is put there, it would not exist. So something like an asymptote would be non-removable, or something like this, which we've seen in class before, would be non-removable. There's no point you can put here that would make this continuous, and no point you can put here that would make this continuous. So how would we identify that? Well, at this point, we're just going to use some pre-calculus knowledge. We're going to figure out, do we have a hole, or is it just a 0 of the denominator? Well, let's look. So if we look at this first one, to figure out where it's 0, we set the denominator equals 0. But a better way to do it is to factor it, because if we factor, we can find holes. So on top, we have x plus 4 and x minus 3. On bottom, we have x minus 4 and x plus 4. So we have two discontinuities. I'm just going to put it there. Two discontinuities, x equals 4 and -4. One of those is non-removable, one of those is removable. The removable one is the one that can be canceled out, x plus 4. So x equals -4 is removable. Think about it this way. We removed that factor from the equation. X minus 4, or x equals 4, is non-removable because it did not get factored out. It's still there. You can do the same thing for each of these. just factor and see. So we have x minus 7, x plus 1 over x plus 1. One discontinuity at x equals negative 1. And it is only removable, not non-removable. There's no non-removable ones. Similar thing down here. We have x squared over x plus 2 and x minus 2. Both of these are non-removable because they do not get canceled out. So x equals negative 2 and x equals 2. Didn't know why I wrote it twice. Okay? The last thing we're going to look at is one like this. Okay? These are a little weird because you have to really think, it should be x approaches negative 2. I don't know why I put that wrong. X approaches negative 2. Yeah. All right. If we look, negative 2 is a discontinuity. When you plug in negative 2 there, you get 0 on the denominator. All right. We're just looking at the limit from the right, though, as we approach negative 2 from the right. So let's think about what's happening. On the top, as we approach negative 2 from the right, we're going to be getting closer and closer to negative 2 on top. As we approach negative 2 from the bottom, we're going to be getting closer and closer to 0 on bottom. Okay? So that means we're going to have negative 2 divided by 0. Well, that's undefined. But what we need to think about is what is the graph doing there? As we approach 0 on the denominator here, what numbers are we approaching first? Well, a square root is only going to give us positive values unless we took the square root ourselves, unless we did it to get rid of the squared. So if we think of numbers before negative 2, on the right side of negative 2, so this is positive 1, 0, negative 1, negative 1.5, negative 1.9, negative 1.999. What's happening here? So 2 plus 1 is 3, square root of 3, some positive number. 2 plus 0 is 2, some positive number. 2 plus negative 1 is 1. That's just going to be 1. 2 plus negative 1.5 is 0.5. That's going to be a square root of 0.5, some positive but relatively really small, really small number. Negative 1.9 plus 2 is going to be positive 0.9. So once again, a square root of positive 0.9 is some really small number that's going to be really small. So we have negative 2 over really small positive numbers. And this is where your number sense really comes into play. If you take a number and divide it by something that's really, really small, so like 1 divided by 0.1, 1 divided by 0.01, 1 divided by 0.001. As that denominator gets smaller, the whole thing gets bigger because you're dividing by fractions. Let's think about it this way. 1 divided by 1 over 10 is 1 times 10. That's a big number, and it gets bigger as this gets bigger. So as the denominator gets smaller, your number is going to get much bigger. So when you have negative 2 divided by a really small number, that's going to be this whole thing is going to be going to infinity. We just need to figure out what infinity it's going to. Well, let's look. We have a negative on top divided by a positive. Negative divided by positive is negative. So this is going to be going to negative infinity. This limit is negative infinity. All right, that's all we're looking at today. Let me know if you have any questions, and y'all have a great day.